Let me tell you about an experiment described by Ronald Fisher, the genius who almost single-handedly created the foundations for statistics. An acquaintance of Fisher's insisted that tea should be prepared by putting the tea in first and then the milk second. Fisher was sceptical that anyone could taste the difference, so he set up this experiment. He prepared 8 cups of tea, 4 with the tea first, 4 with the tea second. Then he shuffled the cups. Then he asked his friend, who didn't know how the cups had been shuffled, to taste them and to say whether each was tea first or milk first. Then he counted how many she got right. She got all 8 cups right. She could conceivably have gotten this by sheer luck, but it's unlikely. So a better explanation is that the taste of tea truly does depend on whether the tea comes first or the milk. Let's be more formal about the reasoning. Here's the approach that Fisher invented. First, let X be the dataset, the observed data. In this case, X is the taster's assignment of labels to the 8 cups. Next, we state what's called a null hypothesis, written H0. This is the default view, the assumption that we'll make unless we see enough evidence in the dataset to persuade us away from it. In this case, the null hypothesis is that there's no difference in taste and that the dataset is therefore just a random permutation of the 8 labels, 4 labels saying tea first and 4 saying milk first. Now, we choose a function called the test statistic. This is a statistic, that's a technical word we learnt in the last video, and it just means it's a function of the dataset. In Fisher's experiment, let T of X be the number of cups that are labelled correctly for label assignment X. Next, we create synthetic datasets. Let's write X star for a random synthetic dataset. The key feature is that X star should be a random synthetic dataset that's generated under the assumption that H0 is true. In Fisher's experiment, H0 says that the assignment is a random permutation, so that's exactly what X star will be. Next, we'll plot a histogram to show the distribution of T of X star. That is, a histogram showing the values we'd be likely to see if H0 were true. On this histogram we mark on T of little x the value of the statistic that we actually did see. And then read off from the histogram the probability of seeing a result as extreme or more extreme than what we actually did see. This is called the p-value. Another word for it is significance level. This is a real mouthful. Pause the video and make sure you've got it. In Fisher's experiment, let's define f of n to be the probability of seeing n or more correct labels, assuming H0 to be true. We can read this off the histogram. It's the area to the right of n. The p-value is the probability of a result as extreme as what we actually observed. And what we actually observed is 8 correct labels. So the p-value is f of 8, which comes out to be 1.4%. Finally, draw your conclusions. The chance of seeing something like what we actually did see, assuming H0 were true, is p. If p is small, that's evidence that H0 isn't true. It's statistical inductive evidence. It's not logical deductive evidence, but it's still evidence. So, if p is small, we reject H0. Fisher suggested using the threshold 5% as an arbitrary cutoff point, and that threshold has stuck ever since. So, this is how a hypothesis test is done. In the rest of this video, we're going to go through lots of examples of hypothesis tests. They all follow exactly these steps. There's a lot of discretion though. There's what probability model we're going to use in the first place, there's what null hypothesis we want to test, then there's what test statistic to use. The point of going through all these examples is so that you get some experience about how to exercise this discretion. There are some people who just want to be told, here is exactly the test you use and here's the code for it, now go away and run it. And if you look up tests on Wikipedia, you'll find lots of recipes like this. I think you should avoid recipes. The trouble with recipes is that behind each recipe there's an assumption about the model, and often the model behind the recipe isn't the model that's right for your data. If you're working in probabilistic machine learning, then building probability models is your trade, and you have to have the flexibility to invent your own custom models. I've seen far too many cases of students and of researchers who blindly use a hypothesis testing recipe because it's there in a textbook, and they don't stop and think about whether it's appropriate for their particular model. Also, the tests aren't hard. All the examples we'll be looking at are 10 lines or so of code, so there's no reason not to roll out your own custom test each time. Still, it is helpful to see some examples so that you know what tricks you could incorporate when you're rolling out your own tests. Okay, so on with the examples. The examples in this video all have something in common. They're based on parametric probability models. Fisher's t-test wasn't parametric. There weren't any unknown parameters at all in what he set up, and his testing approach is totally generic. But in this video, we're going to be working through tests for parametric models, and for models like this there's a general tip about getting started. To illustrate, here's an example question. We're given readings from two groups, an X list and a Y list, and we're asked if the two groups are significantly different. First, we'll write out a general parametric model. This model should be rich enough to express the concept that we want to test. Here, we want to test if the two groups are different, so we'll choose a model that has a parameter delta measuring the difference between the two groups. Next, we need a null hypothesis. And the idea is this. Let's express the null hypothesis, if we can, as a restriction on the parameters in the model. In this example, the question asks us whether the two groups are different, and the hypothesis, there is no difference, is equivalent to saying delta equals 0. Concretely, if the null hypothesis were true, then all readings, both the X readings and the Y readings, would be all normal of mean mu. The next idea is that if we're stuck for ideas about what to use as the test statistic, let's pick something related to the model parameters. In this question, we're interested in whether the two groups are different, i.e. whether delta is non-zero, so let's just use delta hat as our test statistic. Remember, a test statistic can be any function that we can compute from the dataset. It's not allowed to involve unknown parameters, and we don't know delta, but we can compute delta hat, the maximum likelihood estimate from the data. The general idea of the test statistic is that it should somehow relate to the null hypothesis. If the null hypothesis is true, we'd expect to get delta hat close to 0. If the null hypothesis is false, we'd expect to get delta hat further away from 0. So we can use the test statistic to weigh up whether or not the null hypothesis might be true. Okay, this was just some general purpose advice about how to get started with hypothesis testing for probability models with unknown parameters, which is what we're usually interested in. Now, let's actually go ahead and do it. Let's just summarize what we've decided so far. We're going to model our data as normally distributed with these parameters here, and H0 will be the hypothesis that delta is equal to 0. First step in Fisher's procedure, decide on a test statistic. We've decided to use delta hat, the maximum likelihood estimator for the parameter of interest, and you've seen enough maximum likelihood calculations by now to be able to just write out a formula for it. Fisher's second step, define a procedure for generating a random synthetic dataset. And this next bit is very important. It should generate a random synthetic dataset under the assumption that H0 is true. Under H0, all the values, both the X values and the Y values, are normal of mu comma sigma squared. So I'll just fit this model, and I'll use those fitted parameters to synthesize the dataset. In this question, the dataset consists of two groups of readings, X and Y. So when I synthesize a dataset, I have to synthesize two groups of readings. At this point, I'd like you to stop and think very hard about what we've done here. This bit of code, this procedure for generating a synthetic dataset, is the most important part of frequentist inference. What I want you to do is pause the video, think back to the previous video where we found a confidence interval for exactly this question. How did we generate a synthetic dataset for finding a confidence interval, and how is it different to what we're doing here? They are different, and you need to really be on top of things to know which method to use. So pause, look back to the previous video, and come back here when you're done. Okay, on to Fisher's third step. Third step, generate lots of synthetic datasets and evaluate our test statistic for each of them, and then work out the p-value. The p-value is the probability of seeing a result at least as extreme as what we actually saw, namely t of x, y computed on the actual dataset we have, assuming h0 is true. I've got a very mysterious line of code here, line 11, which we do need to unpack. First thing to think about is, what do we mean by extreme? Here's how I suggest thinking about it. First, let's plot the histogram showing what we'd expect to see for t if h0 is indeed true. Then, plot some histograms showing what we'd see if h0 weren't true. I simply picked some arbitrary parameters, generated synthetic datasets using those parameters, and plotted the resulting histograms for t. If I pick parameters where delta is above 0, the histogram ends up further on the right, and if I pick parameters where delta is less than 0, the histogram ends up further on the left. So this is how I decide what more extreme shall mean. If I got a t-value on the extreme right of the top histogram or on the extreme left, either way it's a suggestion that h0 might perhaps not be true. Cases like this, where extreme means either tail of the histogram, these cases are known as two-tailed tests. Next, we want to compute p for a two-tailed test. Let's see how we can do it. Let's just remind ourselves what a p-value is. P is the probability of seeing a result at least as extreme as the observed t, i.e. t computed on our actual given datasets x and y, and it's a probability under the assumption that h0 is true. Here's how we can compute it. First, imagine a histogram showing our sampled t-values, i.e. the distribution we'd expect to see if h0 were true. I've drawn the histogram in the top plot, and the bottom picture is a schematic showing all the individual points that make up the histogram. Mark on the actual observed value of t. Next, start counting in from the extremes. In this case, extreme means either tail of the histogram, so we'll count in from both sides. One item from the left, one from the right, another from the left, another from the right, and so on, and keep going until we hit t. This selects all the sampled points that we generated that are more extreme than our observed t. So what we've found here is that 6 of the sample points are more extreme, 3 on the right, 3 on the left. And this is where the magic formula comes from. The two clauses are for counting what fraction of points are more extreme than t. One clause for if we hit t coming from the right, one clause for if we hit t coming from the left. As for why 2 times the minimum is the right thing to do, I'm going to leave you to stare at that and figure it out yourself, or you could read the explanation in the printed notes. These pictures should give you some understanding of where the formula is coming from. Or, alternatively, you could just learn this formula as the formula to use for p-values for two-tailed hypotheses and never worry again about how it's derived. Okay, that was an awful lot of thinking to understand one small line of code. I want to work through a few more examples now so that you understand the general strategy. Here's the next example. Pause the video and have a read. This question's more involved than the last example where we had 2 groups and we could just measure the difference between the 2 groups directly. Here there are 3 groups, so there are 3 differences that we could measure We could measure it between x and y, between y and z, between x and z. So what should we do with them all? Well, here's something we could do. First, I'm going to start off in the usual way for a parametric model. I'll write out my full model. Here my model allows all three groups of readings to have different means. Next, decide on the hypothesis I want to test. The question asks if the three groups have the same mean, so I'll let my null hypothesis be that μx equals μy equals μz. In other words, if h0 is true, then all values from each of the three groups are normal with a common mean. Call it mu. Next, the bit that takes a creative leap, inventing a test statistic. Here's one that I invented out of thin air. I'm going to measure this test statistic here. Let's look at it. The first term measures the difference between mu hat sub x and mu hat. In other words, the difference between the mean of the x readings and the mean of the whole lot. If all three groups have the same mean, this term should be small. And I'm adding up terms like this for each of the three groups, so if any of the groups is different, my test statistic ought to be able to pick it up. If h0 is false, in other words, if the three groups aren't identical, it will tend to make t bigger, more positive. This test statistic is made up out of maximum likelihood parameter estimates, 3 of them estimated from the general model, and mu hat estimated from the h0 model. It's always a good idea to play around with maximum likelihood estimators if you're looking for inspiration about what to use as your test statistic. Okay, so we're ready to code. Fisher's first step, define the test statistic. This is just turning our formula for t into code. Next step, write a function to generate a synthetic dataset assuming h0 to be true. Remember, h0 said that all values in the whole dataset are drawn from the same normal of mu sigma squared distribution, so I just find maximum likelihood estimators from mu and sigma, and I generate a synthetic dataset from them. My synthetic dataset has to have 3 groups of readings, just as the original dataset does. Fisher's third step, generate lots of synthetic datasets, compute the test statistic on each of them, and then find the p-value. Remember, the p-value is the probability of seeing a test statistic more extreme than the one we actually saw, assuming h0 to be true. What does more extreme mean in this question? We said earlier that if h0 is false, then t will be more positive. In other words, extremely positive values for t are evidence against h0. So we want a one-sided test. In other words, the p-value is the fraction of observations that fall in the right-hand tail of the histogram. Great. The message here is that you can test pretty much anything as long as you have the creativity to define a null hypothesis for what you want and to set up a test statistic that can capture divergences from the null hypothesis. For the next example, we're going to work with some real data. Fires in the Amazon. In the last video, we analysed this dataset using confidence intervals. Now, let's see what answer we get from a hypothesis test. The first thing to do, of course, is plot the data. Then set out our model and the null hypothesis. The time period that the newspapers were interested in is 2011 to 2019. This is because Dilma Rousseff came to power in 2011 and Bolsonaro in 2019, and the narrative is that the uptick in fires represents a policy change by Bolsonaro. So we're only going to model the data from 2011 onwards. The null hypothesis is the default belief, the conservative assumption, the thing we'll believe unless there's evidence telling us otherwise. In this case, I'm going to use as my null hypothesis the model that all these values from 2011 onwards are drawn from the same distribution, let's say normal with mean mu and variance sigma squared. I haven't actually bothered stating a general full parameter model here. That trick I told you about earlier, of first stating a general model and then writing h0 as a restriction on the set of parameters, that trick was only there to help you figure out what you might possibly use as a test statistic. We don't need that help here though, because the question tells us what test statistic to use. It tells us that the media reported the year-on-year increase from 2018 to 2019, so let that be our test statistic. The question actually tells us one more thing. It asks if the observed value of t was worryingly large. In other words, it's telling us what direction to look in to interpret what extreme value means. The question is, between its lines, telling us that a large positive value of t is grounds for rejecting the null hypothesis, for concluding that something has changed in 2019. Okay, now we've set everything up and we're ready to start coding. Here's the code. It's just the usual three-step Fisher procedure for testing hypotheses, nothing special. You should pause the video though, and just make sure that all the code here makes sense. The only thing left is to write out what the actual answer came out to be. Here's what we get. The p-value is 5.3%. Fisher's magic threshold is 5%, and so this p-value is just above 5%. In other words, there aren't clear grounds to reject the null hypothesis. It is borderline though. When it's borderline, it's really an invitation for you to look further, for example, to gather more data. Okay, so that is hypothesis testing and p-values. It's always exactly the same three-step procedure. It's just there's often lots of creativity involved in framing your question as a null hypothesis and in choosing the test statistic. There's also scope for creativity in how we create the synthetic datasets. In this video and the last one, we're working exclusively with parametric probability models where we could synthesize a new dataset by simply plugging in our parameter estimates into the appropriate random number generator. In the next video, we're going to look at a different way to synthesize datasets, and we'll tie up with the earlier videos about the empirical distribution. To finish this video though, a last word about p-values. This is Sir David Spiegelhalter, a Fellow of the Royal Society and Professor of the Public Understanding of Risk at Cambridge University. He's a regular guest on the BBC radio programme More or Less, which delves into the numbers behind the news stories. David Spiegelhalter comes on air and he usually debunks the more extreme claims made by journalists and politicians who don't know how to think about uncertainty. If you're talking to someone and they come up with a conclusion you don't like, try asking them, what's the p-value on that? If they have any scientific training at all, they'll quail and you can tell them, oh, your conclusion isn't statistically significant. Of course, this won't work on people who don't know any science at all and who don't trust evidence. And it also won't work if they actually tell you a very small p-value. If they do, then it's you who has to change your mind. When I hear David Spiegelhalter on air, I always think of him as the Cambridge professor of what's the p-value on that? Although, to be fair to Professor Spiegelhalter, he's a Bayesianist, and Bayesianists don't believe in p-values. They have a completely different suite of tools for reasoning about uncertainty.